Here we are for Chemistry 103. First lab demo will be for this particular lab. All right. Laboratory techniques, using the laboratory gas burner, making laboratory measurements. And what you see before you is everything that you will need to complete this lab. And I'm going to show you how to use each piece that's on this table. You'll notice that we have a Bunsen burner, we have Pyrex tubes, we have a tube holder, and we have tongs just in case. We have a 10 milliliter graduated cylinder, a 100 milliliter graduated cylinder, a 50 milliliter graduated Erlenmeyer flask, and a 50 milliliter graduated beaker. Chem wipes for cleanups. We have a thermometer. We have a beaker for ice water, which I haven't made yet. And we have a beaker of water coming to a boil. What else do we have? We have a meter stick. And we have something to measure using the meter stick. We have 3 balances. This is a balance that will measure down to a 1/10 of a gram. This one measures down to a 100th of a gram. And this one measures down to a 1/10 of a milligram. So figure that one out. Then we have our ice. We'll need our ice for making the ice water. That's everything you need. Well, for weighing purposes, we have to weigh a 125 milliliter Erlenmeyer flask, a 13 by 100 millimeter test tube, and we need a quarter to measure. There. Now that's everything you need. All right, let's go through this one step at a time. First in the method is learning how to use a burner. And first lesson is don't keep anything combustible next to a Bunsen burner. So we attach the burner here. And we turn on the main gas for the room. Now, how does a Bunsen burner work? A Bunsen burner takes natural gas from the supply, mixes it with air, which is controlled by this little device here, the amount of air that goes in, and burns it to produce heat for various purposes in a lab. All right, how do you start one? Turn the gas on. You don't have to turn it on full, just till you hear it. You may be able to hear it, you may not. And then use your striker. Stay lit. There we go. Okay, our burner is lit. And if I hold something behind it, you can see it better. Well, can't see it with that. Maybe white paper. You can see it behind. No, you can't see that either. Okay. So how do you control the flame? The ideal flame is a double cone. This is a single cone, and when you starve it for air, you get that yellowish color, yellowish orange. That yellowish orange color is incomplete combustion. So what happens in incomplete combustion is the methane in natural gas only partially combines with oxygen and converts to water and carbon dioxide, and the rest of it converts into carbon particles. We call that soot. And the soot is heated up and incandesces as the yellow color. All we have to do is add more air. There we go. Now, that flame is a little too high for useful heating. So we'll turn down the amount of gas. Okay. There we go. Now, I hope you can see, if I get the right angle, a double cone, an outer cone and an inner cone. The hottest part of that flame is right at the tip of the inner cone. So when you make adjustments, say we starve it for air, you get the yellow color. And when you give it plenty of air, you get the double cone. Okay, next step. We've got our burner set up, and okay. Next thing we need to do is, after we describe the flame, we take a Pyrex tube, a test tube, put it in our holder so we don't burn our fingers, and we want to put this in the flame and see what we observe. The first thing I observe is condensation. Remember, when this flame, when the natural gas burns, it produces carbon dioxide and water. Well, that water is very hot. But if we give the water some place to give up its heat, it will condense as a liquid. And when the tube is cold, that's what happens. You can't see it anymore because the tube is hot. Okay? So now let's adjust the flame so that we get incomplete combustion. All right, now let's see what we observe. Hopefully, you may see this and you may not, and if you don't, I'll describe it to you. Okay, incomplete combustion produces that soot. So where's the soot going to go? It's going to collect on the tube. So if we hold that up to the light, we should see a darkening of the tube for the soot to collect on the tube. All right, now we're going to put that in here in the test tube holder so that it'll cool down. And then we'll look for that's all we have to do for this exercise. So what do? We just shut off the gas and let the burner cool. And before we go to the next step, we don't need the gas anymore. We're going to turn it off. All right, next step. Laboratory measurements. What type of measurements can we do in the lab? Well, one is we can measure the length or the area or the volume of things directly using some type of measuring device that's been standardized. This is actually 1 meter long. And notice that it's divided up in big numbers into 10 places. 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, what that means is each one of these big ones is a decimeter, a tenth of a meter. But the numbers represent centimeters. So at this point, you have 10 centimeters. 10 centimeters. A centi is 1/100th of. So if a centimeter is 1/100th of a meter, it takes 100 of them to make a meter. So if you go from this end to this end, you will have 100 centimeters. Each centimeter is divided into 10 equal parts, 1 millimeter. So 1 millimeter is 1/10 of a centimeter. And if 100 centimeters make a meter, 1,000 millimeters makes a meter. All right. So first thing we want to do, after we learn what this means, is take your meter stick, and the method says measure your laboratory manual. Well, I don't have one with me, so I'm just going to use this sheet of paper to make a measurement. So I'm going to measure the width of this paper, and we set the 0 mark here, and we look over here and find that we have 21.6 centimeters wide. Okay, so the width is 21.6 centimeters. And notice on this paper, centimeters is the unit of measure. So if you go between 1 centimeter to the next, you're talking about fractional centimeters. So I moved 6 millimeters over, which means 1/10 of a centimeter. That's why I have 21.6. Now let's measure the length. Okay. And it looks like, if I set that right, we have 27.8 centimeters in length. Now, questions in the method ask you to convert those to millimeters and calculate the area in square centimeters. Everybody knows the area is height times the width. So all you have to do is multiply the centimeters of the length and the width to get the area in centimeters squared. But how do you convert that to millimeters squared? Well, notice that when you have centimeters times centimeters equals centimeters squared, if you convert that into millimeters, and you would have 10 millimeters each, and millimeters squared. So 10 times 10 is 100. So what that means is, for every square centimeter, there are 100 square millimeters. So whatever value you have in here for square centimeters, you multiply by 100 to get square millimeters. Or you take your conversions to millimeters and multiply those together to give you square millimeters. Either way works. All right, that's measurement of length. Now we're going to measure volume, direct measurement of volume. All right, let's see. Let's mark my place here. And the first thing we're going to measure is volume. We're going to use water. So I need water. Where's my water? All right, I lied. You don't have everything you need. You need distilled water. Okay, so let's move around here to our measuring devices. Graduated cylinder. I just threw this one in for good looks. We're only going to need this, this, and this. Okay, first thing we do, what is the standard measure of volume? It's the liter. But we rarely ever have glassware that's measured only in liters. It's usually measured in milliliters. So 1,000 milliliters makes 1 liter. And you'll notice that this, let's see, you'll notice this 100 milliliter graduated cylinder is marked off in 1 milliliter increments. Okay? This graduated Erlenmeyer is marked off in, well, let's see, that looks good, is marked off in 10 milliliter increments, as is the graduated beaker. Okay, first thing they want us to do is take a 50 milliliter graduated Erlenmeyer flask here, fill it with water to the 50 milliliter mark. So we fill it to the 50 milliliter mark. Now, how do you know when you have the level of liquid at the correct volume? Glassware is by default calibrated to hold aqueous solution, pure water. That's how they calculate it. So what we have to do is hold it at eye level and make sure the bottom of the curve in the liquid is matching the mark. That curve is called a meniscus. So the bottom of the curve, and we have to hold it at eye level. I need a little bit more. There we go. So now we've measured, we think we have 50 milliliters in this. But this is marked off in 10 milliliter increments. This one's marked off in 1 milliliter increments, which means that this one is more accurate. So we're going to use this one to test that one. Our expected volume is 50 milliliters. Our actual measured volume is what it is when we pour it into this device. And now, we go back over here to our table. Okay. And we say, what value did we get from our 50 milliliter flask? In actuality, we're looking at let's see, this is marked off, pardon me, yeah, in 1 mil increments. So if we come up to here, it's 50. And if we go to the next level, it's actually just below, it's between 50 and 51. Now, you'll know that the uncertain digit in any measurement is the last one. So the certain ones we know have markings for them. So we know it's 50, but it's not quite 51. So we have to estimate the last one. It's almost 51. I would say 50.8. 50.8 milliliters for the flask. Now for the beaker, we're supposed to do not 50, but 40, because the measurement here is for 40 milliliters. So we're going to pour some of this water in, and then we're going to finish it off with better control from our wash bottle. So we need to get down to eye level and hold it level, as level as we can, and bring it up to 40. Okay, now let's empty this flask because we don't want to add it on top of some that's already in there. And then we're going to find out what is the actual value, a measured value from the assumed or accepted value. So the accepted value for the Erlenmeyer was 50. The accepted value for the beaker is 40. But the measured value for the beaker is 39. 39.0 milliliters. So what's the error in our Erlenmeyer flask? The error is 0.8 milliliters. Okay? The error in our beaker is 1 milliliter. Now, how do you calculate percent error? You take the accepted value which is 50, minus, well, actually, it's you take the measured value minus the accepted, which is 0.8, and divide it by the accepted value, which is 50, times 100. Okay, you can do the math there. The other one would be, this is the difference, 1 milliliter divided by 40 times 100. And notice, when you turn in this work, there's a place to show your work, show your calculations. All right, it's worth 2 points. You don't want to miss that. So then you decide which one is the more accurate of the three, the flask, the beaker, or the graduated cylinder. All right, so much for that. Dump that out, dump that out. There we go. Now we're on to measuring mass. So here we want to measure the mass of a quarter to begin with. All right, how do you use one of these balances? These are both triple beams, but the least accurate one is this one, and we're calling this one the platform balance. This one is the triple beam balance. And this one is designated the top loading balance, or in our case, the analytical balance. Okay, so least accurate, next best, the best. All right, first you have to do with these triple beam balances is be sure it's zeroed. So you can see right there that it's set on 0 with no mass on the pan. Nothing in the pan here. This one should be close to 0. It's a little low. So how do we adjust it? We come here. It needs to go up a little bit, so we move this weight out just a little. And then watch where it settles. I think we're good. Okay, now we have a quarter. You've got everything set on 0. All right, naturally, the right arm goes up. So we see, can we get the arm to go back down by moving the small one? Well, that's not right. You start with the big one. Start with the most weight. 100 is too much. Right? 10. 10's too much. Now we go to the small one. We know it's in here somewhere. Okay, so I'm sure none of you have ever used an old style single lens reflex camera where you have to focus yourself. You focus one of those cameras, it's not autofocus, some of them are now, all of them are now, but it used to be when you focused your camera, you bracketed. In other words, you focus too far one way, then too far the other, and you gradually get closer and closer and closer and closer until you're focused. Similar logic here. We don't have enough weight. Let's put some more until we go past the mark. That means we have to come back in the middle where we were. All right. That's too far that way. So we bracket it a little more. And you watch the swing. You don't have to wait for it to get set on 0, as long as you notice that the swing is the same above as below the 0. All right, we're getting close. If you want to wait, we can. I think that's good. We're very close. Okay, now how do you read it? Well, this quarter is not 10 grams, it's not 100 grams, it's something less. So here we have 5, less than 6, greater than 5. So 1/10 of a gram will be our next value, right? 5, the next one is 7, 5.7, but it's a little over 7. How much over is it? It's about 6/10 over. So what does that mean to our value? All right, a quarter on the platform, we have 5.7, and then a fraction of that is another 7. Okay? Now, let's stick with a quarter. Let's go to the next best one. All right. Right, we know that it's going to be more than 5. So that gives us a place to start. Set it on 5, and there's a notch there that you have to be in. And then we start adding weight. Okay, close, close, close. Did I get lucky? I did. I hit it right on the first time. Sometimes that happens. So now this one says it's 5.7, and the next digit is 1. So this one says it's 5.71. Now we go to the next one. Okay. Our analytical balance, all we have to do, it's electronic. We just hit this button. It resets to 0. Then we take our quarter, lay it on the pan, close the door, and wait for it to settle. All right. And then you just read the number right off. On this balance, that little asterisk means it's stable. 5.6382. 5.6382. All right, so that's our quarter. What's next? Test tube. All right, so we're set back to 0. Let's see if the test tube will stay on here without rolling. Okay. Now, is it 10 grams? No, it's less than 10 grams. So let's go out here. That's too much. Okay, come back. You go in the middle. All right. A little too far. Let's back up some. That's pretty close. I think it needs a hair, a little more here. Okay, so I'm going to call that 6.40. It's right on the 4. How about the next one? All right, we know that it's greater than 6. So it's close to 0.4. Let's find out if it's how close it is. All right, that was too far. Back up. A little more to the right. Let's use something a little more delicate than that. Oh, now it's too low. Back up. All right. Just a hair to the right. You can probably see that technology is a good thing. We can weigh things a lot quicker on the analytical balance than we can on one of these triple beams. Okay. And that's very close. Okay, 6.29. 6.297. Okay, so now let's put it on the analytical. It's already zeroed. See that? 6.2922. 2923. All right. One more thing to measure. You can probably guess that this one's going to be a lot heavier than those two guys. There. So let's see. Less than 100. Okay, between 70 and 80. Hey.
You was talking about cooking the books.
Yeah.
Well, Convocation last year, Shields got up there in front of everybody, and we looked at the balance sheet. They gave the balance sheet.
Okay. I'm back. After I was so rudely interrupted. Okay. So this one looks like it's settled down at 72.32. 72.32 grams. Okay. Let's try this balance. So we know it's going to be close to 70 something. 72. Let's see what 3 looks like. Almost. It's kind of like taking blood pressure the old-fashioned way with a cuff. You say, and they just let the air come rushing out of that cuff and then give you a number. See, how did they do that so fast? 72.355. Okay. Now let's go to the analytical balance. Still zeroed. Put it on there. Wait for it to settle. 72.4077. 72.4077. Okay. That's all the mass measurements that we need. And always when you finish a balance, put everything back to 0. 0, 0. All the way back. Why is that? Because these balance arms are sitting on a knife edge. And if they're off center and have extra weight on one side or the other, it'll cause that knife edge to dig into its seat and throw the balance off. And after that, you won't be able to use it. So put it back to 0. Take the flask. We're done with mass. Now it's time for temperature. So let's go around here and do our temperature. All right. Notice there's your thermometer, and it's got a red fluid in it. That liquid in there obviously is not mercury. They don't let us use mercury anymore because somebody's scared of his shadow. So these thermometers are not very accurate, not like a mercury thermometer. Okay, it's been sitting out here, and we can read the temperature. If we want to be sure it's equilibrated, just move it around a little bit to get the air flowing. And then measure that red on the lines. Okay, I don't know if you can see it, but I get 21 degrees centigrade as room temperature. 21 centigrade. Now you need to convert to Fahrenheit and Kelvin. the you're going to get experience in the class, the lecture part, on how to make that conversion. There's a formula converting centigrade to Fahrenheit. Look it up. It's in your book. And converting centigrade to Kelvin. I can tell you that one. Just add 273 degrees, right? So this would be 294 K. All right. Now, this one's already boiling. Let's be sure it's boiling. I'm going to crank up the heat a little bit. While I'm doing that, I'm going to make ice water. So how do you know that you've got the temperature of ice water? Where's my ice? Here it is. The temperature of ice water is stable when your mixture has ice and water at the same time. If all the ice melts and you've only got water, you don't have ice water. Or if you've got ice and no water, you don't have ice water. So you have to have water and ice together. Add more, add more. Actually, there's a quicker way. Quicker way is here. Okay. Now, and this is distilled water. Let's mix it up so we can equilibrate everything. Give it time to melt as much ice as it's going to. And when the ice stops melting, you will have the freezing point of water. Now, everybody knows that the freezing point of water is 32 degrees Fahrenheit or 0 degrees centigrade. But I just told you that thermometer is not very accurate. So let's see what we get. And when you're measuring the temperature of any substance, you don't want to get it anywhere near the container walls, because then you're getting influence from the outside environment. You want to stay as close to the middle as possible. And I'll show you again on the boiling water why you don't want to do that. Right in the middle. Okay, now let's see. Let's bring everything up to eye level and look at it. All right. All right, I got a temperature there. Let me see if it changes after a minute or two of stirring. No, it seems to be stable. That is 1 degree centigrade. Ice water at 1 degree. So you do the rest. Boiling water. All right, that water is definitely boiling. So let's clean this off and let the temperature come up a little bit so we won't shock the glass. This temperature shock can break glass. So we're going to at least bring it back up to room temperature or pretty close to that. All right, that's good enough. Now let's measure boiling water. Mix it up, mix it up, mix it up. And keep that bulb in the middle of the water. If you're close to the edge, it might be too cool. If you're close to the bottom, it's going to be hotter because that's where the heat's coming from to boil the water. So we mix, 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 and hold it in the center. And let's see if the temperature's still changing. It's still coming up. We might have to wait a little bit on that one. All right, let's come back in a second and measure it again. We'll hold that temperature. And that's the last thing we have to do. So while we're waiting for this to boil, it's sort of boiling, but I want a good rolling boil. What do you do when you're finished with a lab? You clean. You never leave a lab in a mess. So you have to clean up everything. You have to properly dispose of any waste. We didn't produce any toxic waste here, right? We just use water, so that can be dumped down the drain. There are some other things that can be dumped down the drain with plenty of water. They're non-toxic. We just don't want them in concentrated amounts. But that's the job of the instructor to tell you what that is. One thing we also didn't discuss at the very beginning was safety, right? In your reports, not this report because it's not a formal report, but in your formal reports, you need a blurb, a statement of safety considerations. So what would the safety considerations be here? Well, first of all, heat. You don't want to burn yourself. Be careful with open flame, right? Don't keep paper or combustibles around your open flame, right? Water's okay. We wouldn't want a squeeze bottle with alcohol in it right next to that flame. What else? Glass. You know Murphy's Law. A dropped beaker will shatter into as many pieces and as far away as possible every time. That's Murphy's Law. If something bad can happen, it will. So you have glass here. You have to be careful with broken glass possibilities. Okay, what else? We have a hot plate. And believe me, that plate is hot. I made the mistake of touching one time. And naturally, I burnt myself. Right? What else? Well, we could stretch it and say electricity. You know, you don't want to be standing in a puddle of water when you plug in the hot plate. But that's all I can see. We don't have any mercury in our thermometer. Don't have to worry about that. We got a pretty good boil going. Let's check this thing and see what temperature we can get out of it. Now, what's the boiling point of water? The nominal boiling point of water is 100 degrees centigrade. But where is that true? That's true at 1 atmosphere pressure, sea level. Are we at sea level? Short answer, no. We're about a half a mile high. So the air pressure here is lower. That means the temperature required to boil water is also lower. Right? So if we were on top of Mount Everest, you could boil water at about 80, 85, somewhere in there, degrees centigrade. Here, we have a temperature of 90. It's over 90. 92 degrees centigrade. So we put down 92. And you do the rest of the calculations to turn in your report. You also have questions to answer. There are pre-lab questions. Let's see, pre-lab questions here, right? Okay. The lecture will teach you how to do this problem where you keep track of significant figures, right? So don't try to answer those unless you've studied significant figures and the calculations that go with them. Then you have all these other questions to answer. And in conducting this lab, I gave you everything you need to answer all these questions. And if you're short on information, look it up. Okay? Some of these questions require dimensional analysis, right? That is, keep track of your units. So when you calculate something, you have to calculate in such a way that units, on the way from one unit to the other, your conversion factors have to cancel the old units and give you new units. And you can do that in a chain if necessary. But all of that is discussed in the lecture. All right. So we're done. Cleanup. What's the cleanup? Cleanup is just get rid of the water, make sure the gas is off, wipe up your area afterwards, and you're done. Well, you're done if you don't have virus scare. So fear of the virus means when you leave, you have to clean your area with some sanitizing material, like the sanitizing wipes, or I like isopropyl alcohol, 70% in a spray bottle. You just spray everything down and let it sit. 10 minutes at 70% isopropanol will kill every virus. So let's just assume that that's been done and it's time to go.